Thanks for coming. It's my pleasure to actually introduce Bodik over here from UC Berkeley. He got his PhD from the University of Pittsburgh and then went on to Madison, Wisconsin for a while before he decided to go to Berkeley and continue his research over there on programming languages, architecture, and anywhere in between. You don't list software engineering, but you've actually published in those venues as well, so you're quite versatile.
I know nothing about software engineering.
Come on. Very humble. Okay, I'll give him the floor.
Thank you, Frank. Thank you for the invitation. It's my pleasure to be here. First time in this department, or in the Triangle Park, or near the Triangle Park. I want to talk today about revisiting a dream that grew in the 60s and 70s, and it was about automatic programming. The idea was that you would somehow write down the description of what the program should do, some high-level specification, the sort of stuff you write in English, maybe not formally, and then you would push a button and the program would fall out and it would do what you want. And that's why it would be automatic programming. You still would have to put in the spec, but that would be it. And the approach sort of was that, okay, let's write down all the axioms and theorems that we need about the domain in question, like sorting. Teach them to the theorem prover, and then if we are lucky, the theorem prover will find the program, and by the way, also prove along the way that the program is correct. And it didn't work for several reasons. One of them was that it takes a long time to write enough axioms, then when it comes to pushing the button, the program falls out, and then the theorem prover wasn't quite able to actually navigate the axioms and give you the program. So the idea sort of worked, but it didn't quite reach industrial use. So since then, many things have changed. And what have changed, let me show you what has changed. So right now, high-performance programmers need to program about, I don't know, 1,000 cores. And it doesn't matter whether the cores are on your GPU or in a big supercomputer center, the problems are more or less the same. It's a big headache. Now, things are going to change, and you'll get maybe 1,000 times more cores that the programmers will have to program. And the things will be hard because there will be more levels of hierarchy. You know, 1,000 more computer means probably 3 times more level of decomposition. In order to achieve energy efficiency, you have accelerators everywhere, both in the data center, both in the supercomputer, and on your phone. And yes, and Amdahl's law is going to haunt you because there will be still a lot of sequential bottlenecks everywhere that you need to work around. And so the programmers will be swamped in algorithmic choices as to what they should implement and how, and it will be hard to wrap their head around it. So the proposal is to turn this Exascale programming challenge into an opportunity, and considering how many cycles we have on the left that we can program, couldn't we take a part of it and put it behind the programmer and help him understand the program? Yes, really help him take the cycles and understand the design choices, help him think about how to write the program, what the alternatives are, and I don't know what. The field is completely open. Let's just think how the cycles could be harnessed to help the programmer. We have already succeeded in harnessing those cycles here for testing, running huge suites of tests overnight for model checking, which explores all possible executions of the program. Just-in-time compilation uses cycles. So there are a few things that help you with programming once the program is written, but not with the programming itself. So here is a challenge for you to think how this actually could be done. This is where we believe the next 10, 20 years of programming will go. Build languages that somehow can harness the computation we have to make programming easier. So to help you think about it, I'll have a little challenge problem. It is a puzzle, logical puzzle, not a program, but as we'll see, it is almost like a program. All problems show up just the same, but because it's a game, it's more fun. So we'll go through that. So there are n players in the room, okay? And somebody will soon come and put heads on their heads. The heads have numbers 0 to n minus 1. There could be duplicates. All heads could be 0. All heads could be number 3. Okay? So the players are in the room and they need to do something. Once the heads are on, they will need to guess the color or the number of their head. Okay? Of course, they won't see the color of their head. They will only see the colors of everybody else's heads. Otherwise, it would be too simple. Okay? And there is another problem that they cannot communicate once the heads are on. So they need to agree on a strategy before the heads are put on what they are going to answer. They need to come up with a strategy so that once the heads are on, at least one of them correctly guesses their own head. Does anybody know how to do that? So this is just the puzzle, but it's a more fun version of what could be a programming problem, especially in high-performance programming where you do various tricks to get your program run fast. The number that you don't see. Well, not every head needs to be represented.
Oh, okay.
So it could be that nobody has a head
okay.
0. Yeah, it wasn't so simple. It was given to us by Evan, one student in our group who likes puzzles, and you like to do synthesis on programs, but yeah, puzzles are more.
If everybody before they put their hats on just says that they will guess a number 0 to n-1, then someone will guess the right number.
I'm not sure that works all the time because you could cover all the numbers, but it could be that none of they are permuted in crazy ways. So we actually couldn't solve this without the tools I'm going to show you how they work. So we started with n equal 2, of course, right? And there are only 16 strategies to consider, and yeah, it's easy to find the winning strategy. So let's use this table to show you what the strategies are. So each player can only see only one head, right? The head of the other player. So each player can see only 0 or 1, okay? And now we need to decide what this player P0 will answer when he sees 0 and what he will answer when he sees 1. Similarly, what P1 will do when he sees 0 and he sees 1. So these are sort of our truth tables. So I can show you that, this strategy here is a winning strategy. There are only 16, so we found it easy to actually fill it on the board. And why this works? Well, let me just show you. Imagine that if, of course, both of them have 0 on their heads, then when both of them are 1, again, one of them will guess right. But let's look at the other case, which is if this one has 0 and this one has 1, then what will this guy answer? Player 1, he can see 0, so he will answer number 1, right? And this player 0 can see 1, so he will answer 1. All right? So one of them guessed, correct. So that's a winning strategy. You can also look at the other case of what if this head is 1 and this is 0. It all works out. Well, but we wanted to solve the problem for any code. It wasn't clear how we could actually look at this and see what it would be for 3. No pattern emerges. And unfortunately, when you go to 3, there is more than 7 trillion strategies to go through.
Well, they could all just guess the same number.
Same number?
If they agree in advance, they all guess 0. No, that still won't work because not
yeah, if they could agree 0, but then the adversary will come and put the head with 2, and then So you won't hold it against me that we gave up and didn't go through the 7 trillion combinations. But what we could do, and we could use the fact that we have many cycles on our disposal. In fact, the laptop is enough. You don't need a supercomputer. And we ask an oracle to give us a winning strategy. It's a strategy that the players follow as before. Now each player can see 2 heads, of course, right? There are 9 combinations that each player can see, but they answer again only the color of their head. Now it is 0, 1, or 2. So that's one winning strategy. There are 10,751 more, but we don't care. This is a winning strategy, okay? So this is how you can solve problems of this kind.
Are the winning ones all 6 permutation ones like this?
Permutations, where do you see a permutation?
Each block of 3 is a, permutation of one of the 3.
Well, they are not always, we'll get there. So you see something which is very interesting that we did not see. So let me hold you for 2 slides, okay?
What isn't? Vertically?
By the way, not all of them. There are strategies where you would not see the pattern that you are spotting. But this is a very keen insight, which we actually needed special help with to get. So this is good. But let me make it now the head more interesting. Because really, if you look at this, you say, you are solving nothing new. Why am I solving nothing new? Because I can do this with existing languages like Prolog. Right? I'm describing the constraints of the game. There could be 27 head combinations on 3 people. Give me a strategy. A constraint solver can find it. And here is a winning one. So there is really nothing new here. What is new is when I change the game this way. Now assume that the players in their communication phase cannot count themselves. You put a head over their head, or you blind them, and they cannot count themselves. And they also don't know what the rank K is. They can only determine their count and the rank once the heads are on, and they cannot communicate. So now each of them, well, now they need to agree on a strategy that is actually a function. The number of players, the rank, and the heads that they see. This is really, a program that they will run once the heads are on. Each of them will plug in their N, K, and the heads. What we did in the previous, I just gave you a strategy for a fixed N. Now I want the program. So that I can run it for arbitrarily large N without running the constraint solver to fill the table, because for large N it won't be able to do the computation. That Prolog oracle will fail. So a plausible strategy seems to be to, well, for the human programmer to look at the table and see what's going on, just like you did, and see whether I can generalize that pattern into a program. So now we are using the oracle to show us a demonstration of a strategy, and we find the pattern and say, oh, I know what this program is. Okay? So the problem was that there were 10,000 strategies, and yes, among them was one that if you look at this, immediately you would see what that program is. A textbook kind of example. But we didn't feel like going through 10,000 strategies to find one that is so regular that you would put it in a textbook. Okay? So that didn't work. So what do you do? The first idea is that you can actually talk to the oracle and say, well, I'm going to constrain you somehow. I'm going to talk to you, and you will answer to me. And the first question is, well, what we did, we fixed this strategy. And we were interested what other strategies for P1 and P2 are compatible with it, in the sense that for any combination of these strategies, you get a winning strategy. In other words, given that P0 decided to play this strategy, what does P1 and P2 need to do to win? And now you sort of start learning about compatibility a little bit of these strategies. And now there are only 8 of them. So great. We sort of pruned down the number of strategies, and we could examine all 8. The pattern was still not quite clear to us. So what we do, we have another tool that looks at the choices made by the oracle and does a little mining on it, and tries to find independent computations. Independent in the sense that, well, what we see is that it turns out that any choice here, and any choice here, and any choice here will lead to a winning strategy. So I could take this and swap it, and it still would be a winning strategy without changing anything in this part of the table. Similarly, I can swap these two and swap it. And similarly, I can take these two and swap them. Right? And this is why you have 8 combinations, 2 and 2 and 2. And this was surprising to us, that indeed what the oracle did is found a combination that really could be composed from smaller sub-strategies. Why is this important? Because I can completely hide this and focus only on this one strategy, since it is independent of these, and understand it much better. Problem is just much smaller. And this is when that permutation occurred to us, that if you look here, this is now a permutation of 0, 1, 2, this is a permutation of 0, 1, 2, and this is a permutation of 0, 1, 2. Only now it really hit us that what it's doing, it's doing some modulo computation of 0, 1, 2, 0, 1, 2. You saw it earlier, but you saw it because I showed you a strategy that was nice enough and had that pattern. In some other cases, the 3 and 3 and 3 were permuted in various ways, so it was not obvious. But once you find this independent subcomputation that can be combined in any ways, it popped up. So, and now we go to the third idea, which is we ask the synthesizer to synthesize that strategy, and they essentially say, well, give me a program, a function over k, n, and hats, that is some program with plus, minus, modulo, and sum in it. Well, why? Well, this is what we got from that 0, 1, 2 modulo. And then we felt, well, maybe those hats, their numbers need to be summed together and combined with this. And plus, minus, well, you throw it in because linear combinations are very useful. This is our clue. And this is indeed what we give our synthesizer in a special syntax, but that's what we tell it. And out comes this function, which happens to be a winning strategy that is general in k, n, and hats. You can run it for any hats, any k, any n. And that's it. So in summary, what we have seen is that you can ask Oracle to not only answer particular questions for particular n, but you can observe what it does. You can interact with it and say, let's fix this strategy. Show me what other strategies work with it. Mine to see what's independent, to look at a smaller problem, and then synthesize a program once you know what operations might be in that program, once you observe that idea. So I want to tell you about the sketch language that we use, which is also embedded in Scala now, in our version of Scala. Because what I spoke to you now is sort of pseudocode in English. There actually is a language in which we do all of this. Turns out that it has only two constructs. The rest is just syntactic sugar on top of it. And here is a think of this as a specification. This is the program that you want to compute, x plus x. This is a hello world example, of course. And here is what we call a sketch. It's a program with holes. It's a hole is this construct here. And what it does is double question mark instructs the synthesizer to replace this with a constant. What constant? Constant that makes this function bar behave like function foo. Which is the specification. Behave really means that they will output the same value. They are functionally equivalent. And of course, you know what the answer is to this question, right? What should come here? 1. It should be 1 because you shift it by 1, you get x plus x. So that's it. There is nothing really else but this. All the rest can be built on top of this operator. And by the way, we can put in assertions which constrain the correctness further. So you could insist on some other properties here. But I'll show you later an example where assertions are useful. I think I will. So what is really going on? This is a different kind of synthesizer that receives a correctness criterion. This is our specification. Right? That was our bar. This is the program which was, I think it was foo. Let's see. Yeah, foo and no, the other way around. And the synthesizer computes the completion. These are the values of holes. You merge them together and you get a complete program. And the reason this is better than the synthesizers before is that what you really do, you just set up a huge constraint system that does not require any domain knowledge, any axioms, and this computes the values of these holes. I'll show you in a few slides how that actually happens. But before that, I want to show you another example. This is actually a real one that comes from a contest we did on what we call sketching in a graduate class. So the student wanted to compute a 4x4 matrix transpose. This seems like a silly operation, but this is what he needed to do in his simulator. And he needed to do it fast, because it was a frequent operation. So he wrote first this specification, which is matrix transpose as simple as you can write, easy to read, easy to validate that it's correct, but it's also inefficient. So he got this idea that he could parallelize it with SIMD. This is, by the way, more or less an example of what you do in GPU computations, except I'm keeping things simpler. And specifically, he ran into this instruction called shuffFP, which is shuffle parallel scalars. And what it does is that you have these two input words, and here is your output word. And special bit masks determine which of these words actually get copied to the output. So you can choose 2 from here and 2 from here, and there is a bit mask that determines which of them go there. And I figure, well, this seems like something I could speed up that matrix transpose. But he was smart. He realized he cannot do it in sort of one step. I cannot take the input matrix and do a few of these operations and get the output. He realized that he will probably need to do 2 phases. Get some intermediate matrix first, and then from that get the result. And he expressed it in sketch language like so. This may look scary because there is a little bit of MATLAB syntax, but I'll explain what it does. So here is phase 1, and here is phase 2. What they do is repeat some number of these instructions. How many? Well, the synthesizer determines how many. The same in the second step. Okay? Now, here you have the input matrix, right, that goes into the intermediate matrix, and from that we compute the resulting matrix. You can see it here, how we go from M to S and from S to T. Okay? And now what do you see in this matrix? Here you are choosing which word from that matrix M you select, and another one, and the bit masks. And this, what does this select? This selects 4 words from the matrix starting at some location. So he's saying, in the first phase, do a few of those, go from M to S under a suitable bit mask, and then go from S to T under a suitable bit mask. Right? This is a pretty close description of his optimization idea. And then the synthesizer, after maybe 20 minutes or so, produce this. It probably does it in 10 minutes today, since this was a few years back. And clearly, you would not want to write these by hand. And indeed, when he did it the summer before, by hand, he said it took about half a day. Whereas once you are somewhat skilled in the language, you write your optimization idea this way. And this is indeed what we hope we'll get out of the sketch language and the synthesis, that as programmers look for optimizations to their programs, either on GPUs or data center or supercomputer, they need to try many different programs. Most of them are thrown away because they don't give you performance. We want to accelerate that process of throwing it away, but really testing it first. So I showed you just this question mark, which is replaced by constants. They could be bit vectors, they could be numbers, but you can build other constructs on top of it. For example, imagine you need just the right array expression. That is some constant times I plus some time constant j plus constant. You just write it that way, or you package it in a macro. Or polynomial of degree 2 can be written this way. There is actually a nice recursive formulation. Or the way we computed that strategy in this heads game is that strategy was a function, right, from some input which you can use as an index to here, to the output. And here are the choices for the strategy. This is essentially a table initializer. So the oracle can compute for us, can initialize the table, and that's the strategy. So here are the values that you saw previously in the table in that heads example. So how is this actually solved? So I started by saying the previous synthesizer in the 70s were efficient. They worked well once they had enough axioms and they could derive the program. We are saying we are not going to derive it, we are going to compute it because we do not want to write down these axioms. So how does that work? Well, so first let's realize what is this sketch, the program with these holes. You can think of it as a description of a huge space of alternative programs. Alternative implementations are, you want to find in that space at least one that is correct, meaning it's the same as the specification. Right? So we are doing this sort of search, but we do it as constraint solving. So we'll start with so-called inductive synthesizer. Inductive synthesizer is something invented in the AI in the 70s. What it does, imagine that we play this game. I give you an input-output pair, and you are supposed to give me a function that agrees with the input-output pair, and also, by the way, is correct on all the other input-output pairs I have in mind. Then I give you another input-output pair, and maybe you were wrong, and you give me another function. And eventually, if that function is from a reasonable class, like a polynomial, we really quickly agree. You soon give me a function that agrees with my input-output samples. That's inductive synthesizer. We'll do exactly the same here. What is the sketch? The sketch describes a space of functions, programs. And now I'll give this inductive synthesizer one input, and I'll ask it, Just give me a program from the space described by the sketch that runs correctly on this input. Does what the specification does on this input. Right? And it finds in this huge space, I don't know, 10 to the 70, one such program. Right? The set of observations are the inputs that they'll use to set up that constraint system to ask for the function that agrees on, that works correctly on that input. Now what happens? Well, either it tells me no program in your space are actually correct on this input, and in which case I know that the sketch is buggy, there is no way I can complete it. Or it will give me a candidate program by the virtue of finding the values of the holes, and then what do? I send it to a verifier or a checker, and this could be a tester, could be a real verifier, and what it will do, it will check that the program works correctly on all the remaining inputs. Okay, and now what? Well, if it's correct, then I'm done, but I'm usually not so lucky after one iteration, so I get an output. What do you think you could get from here that would be really useful?
Counterexample.
Counterexample, exactly. So you get the input that proves that the program is incorrect. You get an input that shows that the program produced so far is not quite correct. You add this input into this set of observations, and this is the second input that I had in mind, or the system has in mind. And now you ask for something that is correct on these two inputs, and you iterate until you have enough inputs to force the inductive synthesizer to give you a program that then passes verification of all the other inputs. And the beauty of it is that, well, each of these can be set up as a set problem, which now have quite good solving skills. But what's interesting is that if your space of programs is, say, 2 to the 300, you only need about 30 iterations of the loop, only about 30 inputs to constrain it enough. So that's quite impressive, and this is why it works really well. So to drive home the power of this algorithm, let me go you through 3 options, right? You could object, you don't need any of the fancy algorithm. You don't need it because, well, you in fact don't even need a sketch. You could say, if here is a specification of what the program should compute, I could just go through all programs in a given programming language. I could start from tiny one and grow it and grow it and grow it and grow it, and eventually you run into a program that computes what the specification computes. Modulo functions that are not computable, but never mind. So the problem is that even if you have a tiny sketch of, say, concurrent list, may have a space of 10 to the 30 candidates, not very large. If you tested one in one CPU cycle, it would take you the age of the universe to find the correct program in that space. So you cannot just explore all programs in a given programming language, starting from the smaller to bigger. So the power of the sketch is now obvious. It reduces that candidate space, because it says don't search all the programs, only search those that meet that sketch constraint. In fact, only look for the values of holes. And so for this example, which I didn't show you, the size would go from 10 to the 30 down to 10 to the 9. And now, even if it takes you a second to do validation, now we are talking about the reasonable synthesis time of about 100 days. Still not reasonable. But if you now add this algorithm, which I just showed you, all you need is just 3 iterations of the loop to solve this example. A minute, maybe 10 seconds by now, if we ran it on the current system, which keeps improving. So this shows you the power of not exploring all programs, but only the sketch, which uses the programmer intuition about what the program should be by pruning that space. And here is the power of counterexample and set solving by finding just the right inputs on which you do the inductive synthesis.
I have a question.
Yes.
So you were saying you didn't, compared with the early automatic programming, you didn't know you'd write down the axioms and whatnot. But isn't that just what your checker is?
Well,
its structure is the set of axioms that you're giving.
Well, that would be nice. Okay, so let me repeat the question. So you understand that this is not based on axioms,
yeah,
right? And this is the more important part. By the way, the way this happens is that you take a program, and in order to check it, you need to finitize it, which means you say, all my inputs will be of up to size 5. And that allows you to unroll the loops. You get a cyclic program, turn it into a binary function, from which you turn it into CNF clauses, and set solver solves it. There is a lot of cleverness in it, but that's the idea. here you say, how do we check it? We typically also check it only on the small world assumption, which is, let's assume the program runs only on up to inputs of size 5. Okay? If you want to do better, you cannot do it automatically, right? Because the problem is undecidable. So we do have verifiers for some domains where we do check it for all possible inputs. You could do this interactively. The beauty is that it doesn't really matter what you do here. It only influences what correctness guarantees you do. You could do random testing. You could do...
But the notion of being correct or not is what the actions were there to say. So that's exactly the function being here.
So let me, if I relax the notion of what correct means, I have a specification, right, which is executable, and I have now the candidate implementation, which is the sketch completed with holes. And now how I can compare them. If I really care about comparing them on all possible inputs, then you do need to do theorem proving, obviously, with some axioms. But we typically just do the verification on the way model checking does, under the assumptions the input will not be larger than, say.
I'm not talking about the method by which one derives that it does it. I'm talking about where is that information being stored, and that is what the structure of the checker is. It's the content of your axioms for whatever size limit that you've placed on it.
So the verification boils down to taking a program like this, which is a candidate value plugged in, and ensuring that it is a function that is equivalent to that.
And where does that knowledge come from? That's what
this comes from the programmer. The programmer provides both this and that, and then the system creates this candidate implementation.
No, but to check that that satisfies the sketch and the spec, that involves the knowledge of what differentiates an incorrect completion from a correct.
So what we do, imagine you have acyclic program. You just turn it into Boolean functions, each of them, and you check equivalence of Boolean function, which is decidable on a set solver, and that's it. What it means to be equivalent, you need to understand the operational semantics of the language, if that's what you mean. You need to know what is the meaning of left shift. You need to know what's the meaning of plus, of course. So that's built in the system that translates these programs into binary Boolean functions. Is that what you have in mind?
Why don't we continue?
Good. I think there is some maybe fundamental, but I would like you to understand it. So, okay. So what I showed is sort of a synthesis that builds programs. What we learn often is that you don't know enough about the problem at hand to actually start writing these sketches. And so what you really need is to work with examples. Examples are really powerful because what's your memory of the red-black tree? Is it this code or is it this example? Okay. If I look at my colleague's napkin when I see him working in the kitchen in PowerLab, it also is an example. He's not developing an algorithm. He's trying to figure out how to move the computation around so that the right thing happens. Right? When students come to a professor to get help with an algorithm problem, he doesn't get as a hint a piece of pseudocode. He gets a piece of execution, an evolving state of the program, which is also an example. But, you know, where does Jim Demel go when he needs help? There is nobody smarter in the PowerLab kitchen that he can ask for help. So wouldn't it be nice if programmers could, so since they work in terms of examples, could essentially work with examples provided by the Oracle, okay? And the Oracle provides insight, as we saw before in the strategy, and then you write the program by making the demonstration of the Oracle deterministic. Okay? So let me now add into our language one other construct, and it's called Angelic clairvoyant choice. Imagine that you run the program on a particular input, and you come to this construct where you ask an Oracle for a suitable value. Okay? So if I give you this bang bang and a set of choices, the Oracle will choose one from them such that the program can terminate without failing an assertion. Okay. Why is this different than what we saw before? Why is this different than the question mark? Can somebody see the important difference? So when I use this question mark or the sketch language, what you see is that I'm forced to write something like this. Right? They say, well, here is an array expression, and I know what I need here is some value times I plus some constant. And the synthesizer will replace it with, I don't know, 3i plus 5. But often you don't quite have the knowledge to put here this template of what the expression should be, because you just have no clue what that syntactic template should be. Should it use I? Should it use j? Should it be a polynomial? Should it be something else? And considering you have no clue, you cannot write this sketch. You just don't understand the problem enough. But what you can do instead is write this. And you say, well, give me some suitable integer. And the oracle, when it reaches the point of the execution, it doesn't need to look for a polynomial, it just gives you a suitable value. So it has much more freedom. Right? And so it now can finish the program, and you look at the values and you see, oh, I see. Those values computed by this angel I can now replace with a polynomial over some variables once you see them. So it's really giving you traces of executions and therefore examples. It's much more flexible, therefore helpful in the early stages of the development. So let me show you how this could be used. So imagine you have a depth-first search traversal of a tree. Clearly it uses the default implementation, uses a stack. It goes down the tree and it needs to know where to return. So it uses linear space. Now imagine that you want to build a DFS algorithm that uses constant space. Because if you want to use DFS in garbage collection to mark reachable nodes, you cannot ask for linear space since you just ran out of memory, obviously, right? So you need something that uses constant space. So how would you do it? So what I'm showing you here is sort of depth-first search with this explicit stack. Usually you write it in a recursive fashion, but this is one that is iterative, right? It does iteration. And here it descends into children. So it pushes the current node into explicit stack, and it sets the child to be the current node, and here it pops. You don't really need to understand the rest. It's iterative rather than recursive because you don't want to use the call stack as a stack. Okay? And now what we want to do, we want to see if we can turn it into a DFS traversal that can live with constant amount of space. So this is what we do. You invent, as a smart programmer, the idea of a parasitic stack. It's a stack like normal stack. It has push and pop, but it has this additional feature that it uses the storage from the underlying data structure, the one that you want to traverse. That's why it's called a parasite. It will borrow the memory, use it to implement its push and pop, but of course it will return it before it is done because parasites don't kill their hosts. They would be toast pretty soon. So it borrows the memory from its host. It has this usual stack and push and pop interface, but it has this parasitic channel. You essentially need to give access to that stack to the underlying data structure so that it can implement its push and pop. So the semantics is just as before. Push X, pop will return this X, but you give it some list of nodes so that it has access to the underlying graph. So when we started working with this, we were not clear whether you can take this DFS and convert it into one with constant space, which would be a major optimization. We had the idea of parasitic stack, but we didn't know whether it will work out. But we could ask angels whether the idea was sound or not. So what we did here is we rewrote it into parasitic stack. You see this is parasitic push and parasitic pop. We give it these extra variables. Why these? Well, so this is a list of these two pointers that are live at this point. At this point of the execution, we simply have these two pointers to the graph. At this point, only this one is live, so we have only that one pointer. So at the high level, all we did was change this. Call the parasitic stack versus normal stack and give it access to the graph. The rest is unchanged. Beautiful interface. All the optimization happens within the parasitic stack. You don't need to touch this at all. Now, what are we going to do, right? How does the parasitic stack work? We'll give it a chance to borrow these fields. These are the pointers to children. These are the things that we can borrow. Right? There is nothing else we can borrow. There is one index which we are going to use. Right? It is the one that remembers into which child to visit next. This is not as important. Okay? So we are going to borrow these child fields. So what I want to illustrate is how having this angelic power allows you to think top-down and simplify your reasoning. And see whether you can implement something as sophisticated as parasitic stack. Okay? So what are the decisions we need to make? We need to decide, when you call push, which of these locations to borrow. Clearly, the traversal at the outer level must not need it until we return it, because it would break the graph and the traversal. But we didn't know which one it is. We need to know how to restore that value in the location so that we don't kill our host. Right? The parasite must not do it. So we need to find out how to restore it. So we need to remember the value that goes in it so that we can restore it. And also we need to, of course, figure out how to use the borrowed location to implement the push and pop semantics. Okay? So all this, we are going to actually ask these clairvoyant angels to implement because we did not have enough global understanding of the algorithm to do it. So let's see how we do it. So this is probably the most interesting slide here. I'm going to implement this parasitic stack, but with this angelic semantics because I didn't know how it would actually work. So let's see how you would think at high level angelically. So first, we know that we can use constant storage, so I'll create one extra location, sort of a temporary location in this stack. It's constant one. We'll need it. And now I'm going to do push. So remember, what does push get? It gets node X that needs to be pushed, and then the list of nodes. The nodes point to objects whose children we can borrow. Okay? So now what? Now we need to decide what location we are borrowing. We need to borrow some location in some node N for some child C, but we don't know which N and which child C. But we'll ask the angel to choose one of those nodes, and we'll ask it to choose a suitable child. So we'll choose a child from 0 to N, the length of the child. So remember, I'm not putting here any logic on which should be chosen and which should not. We'll call the oracle. Oracle will give us a suitable pointer. Clairvoyantly, so that the other angels will call still can finish the work. And this is the level of thinking I want to do, not more. I know I need to borrow something here, I'll decide what. So now, this V, value V is the value in this borrowed location. We presumably need to read it and store it somewhere because we will need to restore it later. Right? That much we knew. And now the interesting stuff comes, right? We have 4 values on our hands. Okay, what are they? There is value in E, value in X that we need to push. There is N, the node that we borrowed, and this value V, right? There are 4 values. We should keep those values somewhere, but where can we store those values? Well, we can store one of them here in this borrowed location, and the other one we can store here. So we have only 2 locations. So we are juggling 4 balls. When the music stops, 2 of them will fall on the floor, inevitably. And we don't know which ones, but we know we can only store 2 of the 4 values. The rest we'll need to get from somewhere else. And we had no clue as programmers, I can tell you how to do this. Okay? So what we do, we write it this way. We say, this is a parallel assignment. So we're assigning to this and that simultaneously, as in Python. Here are the 4 values. And we'll ask the angels to pick 2 values and assign to there. So there is angelic permutation. They just pick the right values and assign them there. And we can observe which ones they do when we run it. Okay? So you see the high-level thinking. Now pop is similar. When you call pop, you decide what is it that you actually borrowed. And again, you ask the angel, what is it that we borrowed? Here is the value that was stored there. And now you need to do 3 things. Select the return value, which is to implement the semantics of pop. Restore the value in the borrowed location and update this extra location E, and we do it in the similar angelic permutation. Okay? So now, isn't this cool? We have a program that encodes our high-level algorithm. I can create a sample input. The program is clearly incomplete. We don't even know whether it works. But it encodes an idea. So now I can run it, and if the angels tell me that they can't finish the program, then what? then clearly I can finish it either, because there is already some problems with it, right? If they can, then I can't either. If they finish, then they show me a sample execution that I can see how they actually manipulate the host, how they borrow, return, and implement stack, and say, ah, I see what they do. And you see there were quite a few choices they could make, and I'll just copy them and do the work. Okay? So let's see how you would run it. So here is this stack without the comments, push and pop together. First, we are going to look at this. We create a sample graph on which we run it and observe the execution. We look at these choices and see, ah, this is what they do. We make them deterministic because we see what the angels do. Now we look at that angel here and observe what it does. It chooses node 0, the first element from the list, okay? Now we look at these guys, and these are a little bit more tricky because they always pick a different value since they go through different children. But if you look into the top, the graph traversal, which calls the parasitic stack, you will realize that this C that is chosen is always the same as n.idx at the level of the graph, and so you just replace it with that. This is the human insight that you get. And what you have now is the complete deterministic program that you want, no angels. You do not want to run angels during the production run, only during the programming. So that's it. So now you see how we used angels to encode high-level reasoning about the program, your ideas, run this incomplete program, observe it, get a final program out.
The question, how did you decide, or who decided which order you pick this variables? I mean, you kind of select, it seems to me that you were selecting this variables in some greedy fashion, per se, to say.
Right.
So, but that may have.
Yeah, so the question is very good, and it is, how did we decide to first observe these angels and determinize? How did we decide to observe those angels and determinize? And indeed it matters. Well, let me tell you the complete story. When you run this program, there are actually multiple executions the angels can do. Some of them do correspond to this algorithm, and some are what we call undesirable and abusive. These angels sort of coordinate in such a way that, oh, I'll break your data structure here, and I know the angel later will fix it. They can do it, right? Because this guy can break it knowing that somebody else can fix it in the future. Remember the mining that I told you before, how you can observe the executions done by the Oracle and find these independent computations in them. Independent computations are those where these angels cannot coordinate and cannot do such devious stuff. So this is after you run this and you filter out those traces where they coordinate, those little sneaky guys. Then you get essentially what I showed you, and at that point it's pretty much independent, doesn't matter in which order you go through. But this mining and the filtering out of these noisy traces is important here as well. So what we got, essentially we derived Deutsch-Orvedi algorithm, which is known as pointer reversal or pointer flipping. But we did it not by breaking the traversal itself, but by isolating all this logic under the push-pop interface. Okay? And making it sort of cleaner and use top-level reasoning about our algorithms. So this is essentially what happens in this algorithm. As the DFS traversal goes down like this, you set up your pointers to point like that. And this is your backtracking structure. This is the stack that you implement. OK. So I promised to tell you about how the synthesis actually plays out at a bigger level. This was all about small programs, data structures, libraries. Of course, not all programs are small. Some programs are big. In fact, many programs or most programs are written by combining libraries together. So let me show you how synthesis will help you there. So when I was teaching this compiler class, I knew I have Eclipse. I knew in Eclipse there was a Java parser which would give me an abstract syntax tree, and I wanted to find the 3 lines of code I needed to open a Java file, get the abstract syntax tree out because I needed it for programming assignment for my students. Well, after 4 days of trying, an hour every day, I still didn't know how to open a file and get an AST. Then I asked my students, and they could do it in an hour, but still doesn't seem like a very productive way of writing 2 lines of code. So why is it? Well, here is the code. And why was it so low? Because, well, there are 2 levels of file handlers. iFile and compilation unit, I expected 1. Okay. There are 2. There are 2 unknown classes. Well, the AST we could guess, but Java core, none of us got an idea to look into the Java core documentation for the right function. And when all failed, we used grep. And grep didn't work because this AST parse compilation unit actually returns a subclass of AST node, not an AST node. So searching for AST node in documentation didn't turn out anything. So there are sort of deep reasons why human programming over these APIs doesn't work really well. So what do we have? We have a problem in which we have an API with hundreds of thousands of methods, which was Eclipse. And the solution is based on two observations. One is that many of these code reuse problems, where you want to sort of glue API together, can be phrased in this following way. You have a pointer to class foo. Imagine that this is the pointer that you have. And you want to obtain a pointer to class W. This is the one that you want. So it's sort of a generalized type conversion. So you can pose that question to the synthesizer as want pointer has pointer. And the second observation that many answers to these questions are not general arbitrary programs, but chains of function calls, of unary function calls that take one argument. You can ignore other arguments, make it unary. Point is that it's enough to get the chain very often, maybe 75% of cases. So the synthesizer for this problem is really simple. You build a graph, directed graph. There is a node per class. There is an edge going from class to class if you can have a function that converts from this pointer to that pointer. And this jungloid, this chain of calls, is just a path through the graph between this want pointer and have pointer. Okay? There are too many of them, but the heuristic which finds the shortest one is usually pretty good. Okay? The second question, how do you package this synthesizer to users? Turns out that you can put it where autocompletion is used today, right? Autocompletion is something that tells you what code you can call at a particular point. So imagine you want to initialize this variable AST. Your cursor is here. Okay? Now look at this. This is the want type. Right? You want something of type AST. You have two variables in scope. These are your have types. So now you can issue two queries. How to get from iFile to AST node and iEditor to AST node. The synthesizer gives you a bunch of these jungloids. You rank them based on heuristic values, and you show them here. And here they all look like they are the same, but they are different instances from different subclasses. So they really are each different kind of code. The point is that the programmer can now examine them, see what class they belong to, what names they have, and usually pick the right one even without reading the documentation. So this is synthesis for API programming. Imagine you have written your library, maybe it's synthesis. Now you want to synthesize client code. It looks like this. Is this different than what we saw before? We saw, well, our synthesizer took a correctness condition, a partial program, or a sketch. Holes are computed, merged, and you have the complete program. So let's see whether this is any different, in fact. And I say it's not really. Your correctness condition here is you're saying, I want some code that goes from have type to want type. The correctness conditions are weaker. All you are saying is that it will type check. It has the right check at the beginning, right type at the end, and good types, matching times at the beginning. So all you are guaranteeing is type safety. Okay? Not correctness condition, because at the scope of this problem, you cannot do better. The partial program is what? We are saying there is this jungloid. We are saying our sketch essentially is only synthesize these chains of calls that restricts what programs we generate, sort of like our sketch. And on the output, we have ranked jungloids. And then you show them to the user, and the user does the final selection. And essentially, the user now completes the specification of what you want to synthesize. Before, you would have to have complete specification here. But imagine how you would specify, I want to open a Java file and get an AST out. Specifying it formally is hard. It's much easier to rank the list and ask the user to pick which function they want. So delay part of the specification later. But otherwise, it is the same synthesis with partial programs. And the synthesizer, yes, is different because it's the shorter path search on the graph, but that's again appropriate because we are talking a different level of programming. So to conclude and to show you that all this can be generalized for end users, because who cares about programmers? These are geeks like us. Who cares if they spend nights debugging stuff? But we would like to help users like our parents. And this is the work that generalizes it. In fact, it sort of started the whole movement rather than generalizes it. But I sort of dreamed up a better version of the system. That's why there is the star. And I'll tell you how it could be cooler than even Tessa did. So the problem is this. Editors are powerful. You can program them with macros. But even people like us have a hard time writing these macros. Forget end users. Okay? So wouldn't it be nice if the user demonstrated the editing task? Okay? Say moving addresses from one point to another, or editing bibliography. And she repeats the demonstration until the macro that is learned is unambiguous. And ambiguous is defined conveniently as, well, maybe there are many plausible macros, but no matter which one you run, all will process the rest of the file in the same way. You don't care about other files. You just care that you demonstrated enough to finish the job on this given file you have in front of you. And there is a solver that is based on version space algebra, which is a sort of less constraint solving, but more scalable way of solving such problems. So here is what they do. Imagine you have a tier of bibliography here, and you want to edit it into LaTeX bibliography. So what you do, you sort of move your cursor here, and you then select a piece of text, and you paste it there. Then you move it somewhere else, and you delete something. You get the idea. Okay? So the system observes this demonstration, which is a concrete trace of execution. The cursor starts in this coordinate. The buffer has this content at this point. The clipboard is empty. Then the cursor goes somewhere else. The buffer is this. Imagine that you have this full record of the execution. Then the system actually wants to obtain what? The system wants to obtain a program that is a true program. Remember, we needed a strategy that was parametric rather than fixed. So you want a program that says move to after string $sign A. So you need to, from this concrete specific trace, generalize into this program. Now, is this also the same kind of synthesis that I showed you? Well, it is. Right? If you look at what the system does, it essentially writes such a sketch. It says the demonstration is some number of steps. You repeat the following some number of times, and the synthesizer based on demonstration selects what it is. In each step, it decides which of the statements the user had in mind, move, insert, copy. For each of them, it decides what you want to insert, a piece of text, or some piece of text indented a little bit, or it moves it to a location, and the location is defined recursively as, well, you want to move it to some offset or a row and column, you get it. It's also a sketch, describes the space of programs are solved, but they are solved slightly differently, right? The correctness criterion is now the demonstration. What you get must be consistent with demonstrations. You are not saying, the user is not telling you anything more. There is no other correctness condition, but that's fine. There is the macro template which you just saw. The output is a set of macro parameters, essentially the values of these holes. You get the completed macros in, and now what do? You run them, okay? And you run the macro, right? Then you run the second macro, the next macro. You run all of them. If all of them produce the same file, you have converged. The user has demonstrated. Now, if some of these processes the file differently, you need to ask the user for more demonstrations. Otherwise, it's the same. You see the creativity on how you can define what this program is, what's a correctness condition, in other words, where the constraints come from, and where you actually refine the specification. You don't need to get it right away. You can iterate and talk to the user, get for more of them. And perhaps most importantly, this shows how so many different tasks are just programming, right? And how the demonstrations, which demonstrate something like, that looks like programming, macro creation, can be phrased as this synthesis problem, constraint solved, and hopefully make the lives of users better. You can apply this idea onto creating web mashups by demonstrations and so on. So what we have seen is partial programs essentially can communicate to the computer what the human inside is. If you believe that the algorithm works like this, except you don't know some details, you can write them. You can ask the Oracle to complete them, either give you a trace or give you a complete program. We have a bunch of algorithms that can complete the mechanics of that inside, essentially solve it. What synthesizer you use depends on the domain. And end-user programming, API-level coding are decomposable into this partial program stuff with holes and the completion. So the hope is that you can find other domains where this is useful as well. And yes, there are many more ideas on how you take CPU cycles and let the user ask them question and find ways for the CPU to talk back to the user. So with that, I'll stop. Thank you.
Questions?
Yeah.
Yeah. Do we have any questions from the remote sides? I don't know if they can hear me. Maybe you can repeat that.
Other questions from the remote side? You can raise your hand. I think they are waiting for your question, right? In the sort of sketch system on which I spent the first part of the talk, the synthesizer cannot produce anything incorrect because there is the specification. If the sketch is buggy, if it cannot be completed to behave like the specification, so the synthesizer will tell you no completion of the sketch behaves like the specification. Now, yes, you could of course make a weaker specification, not full correctness, but just some assertion. In that case, of course, it could give you a program that. So this sort of the relaxing of holes with angels, which have more power, and then tightening, and seeing where things break down is the way to do it.
Let's say if I want to find an algorithm, not only I just want to find an algorithm, but I have an additional constraint that I want to have a best algorithm which takes the shortest time. So can your approach help in this way? Like for sorting, I need the best algorithm for the sorting which takes the least order of time or something like that.
So we can indeed express some resource constraints, such as the number of steps taken, the number of memory used, and so on. The way it would work is that, remember how I told you that you can put assertions in the program, and the synthesizer will only give you a program that does not violate assertion. Okay? So what you can use these assertions for example, you can count the number of steps, some steps, comparisons, for example, in sorting, and insist that at the end of the execution you don't have more of them than n times log n. Yes, n will be replaced by a particular n. Then the synthesizer, among the choices, will give you one that does not exceed this bound. So these are the options we have.
So it's, let's say if the user himself does not know what the bound will be, or what would be a good bound for the program.
Then we have a recent option that I didn't talk about, and that is find one that minimizes the number of steps. And so the synthesizer will try to create a tighter and tighter bound and give you the smallest one that it finds.
So yeah, that was my question. Can synthesizer do that? Minimize every iteration?
It can. Of course, it will not answer to you in terms of no. It's pretty quick because once it finds the first solution, finding the next one that are tighter and tighter is actually surprisingly fast because it has already learned a lot about the problem and it keeps this knowledge. Yeah. It will not answer to you saying, "Oh, the complexity I found is n log n." It will tell you, "Here is the program that minimizes the value." So that sort of high-level algebraic reasoning it won't do. But yeah, it does what you want.
So does Jim Demel think this would be a good way to auto-tune, for instance?
Well, Jim Demel works with us. I'm not sure he's completely convinced we can do the advanced algorithms that those guys are working on.
Well, auto-tuning the BLAS is not really very advanced, right? It's sort of
well, so this is why he's been talking to us that he wants something from us for a few years. That auto-tuning is not by itself too difficult. Yes, you need to do hill climbing and such.
Yeah.
But generating those programs that you auto-tune over.
All these unrolling parameters seems like that might be, I don't know if the unrolling parameters fit it.
Well, I would say that deciding whether you unroll twice or 3 times is better left to just exploring the space. But you may want to create one version of the algorithm and another and another and another.
Yeah.
And this is where we can help make it easy to generate versions of the algorithm. The tuning of parameters, you should just do through auto-tuning. So you can think of this as this auto-tunes for correctness, gives you a correct program, and then auto-tuning auto-tunes for performance by playing with tile sizes and so on. Same thing. So you know how Sketch describes a space of programs. That has the benefits that you look at the space program at once. If there is a solution, you find it. Okay? But if that space is really large, you get a set formula that overwhelms the solver. And then you are sort of hosed. There are some ways how we can do it modularly. Genetic programming, what it does, it also explores a space of programs, also defines syntactically, right? But how do you create those candidates? You have 100 of them. Now you have your mutation transformations, which create another 1,000 of them. You pick good ones, you create more. And so it's also a syntactic space, also search, but you need to have those genetic transformations to generate that space. If you can find them, in a sense, it's better because you can gradually explore the space. But it's a little bit of an art how to create those.
Yeah. I mean, in a sense, I mean, when you have the feedback to incorporate the counterexamples, that becomes even more difficult with dynamic optimization problems in genetic programming.
Yeah, I don't know how you would use these counterexamples there. Yeah, I think it's, let's say, it would be a great idea to combine the two together if we had the time. Yeah, I think you could improve on both techniques by marrying them. So a question.
I was just going to ask, can we experiment with the sketch?
Excuse me?
Can we experiment with your system?
You can experiment with the system. In fact, my group spent a week last week at MIT with Armando, who is a former student and now a professor there. And we created a new version almost. It will be on the web, so you will be able to experiment with it without even downloading it. I'm not sure it's quite there yet, hopefully in 2 weeks. So there will be some tutorials for you to just click on and play with it.
So are the synthesizer and the Angel, are they proprietary, or what's the...
But the algorithms that are proprietary, no, you can download the whole thing.
Okay.
It will be on the web so that you don't need to install it, but you can download and try with it, yeah. And not all the advances here are released because some of them are messy, but if you want them, send me an email, I'll give them to you.
So, don't you think the performance tuning will become harder and harder because you have actually taken the the control from the programmer? He probably only understands the specifications and constraints, and he gives those, and someone else actually writes the program. So tuning for performance, given the underlying hardware system, will become difficult now.
Well, I think you're assuming that somebody writes the specification and somebody else writes the implementation. That might happen in the future, but for now we really assume it's the same person writing the spec and the program. What we really envision is that the person who currently writes those GPU programs by hand and needs to debug them by hand will be aided by this tool. And so I still assume that that person will have the same understanding about the GPU and the programs, the bugs and all this. I don't think that we'll elevate it to such a level that you won't know what's going on underneath. You should be so lucky, but I don't think so.
And I had another philosophical question. So do you think it's a good way to teach undergrads how the programming is done?
I think that actually this Angelic way of thinking might be useful because it allows you to really go top down and say, here I need to do something. Here I need to rotate, or here I need to balance the tree somehow. And initially you ask the angels to do it. Or at least you can think of it as somebody else does it for you. And then you can drill down and see, well, how do we rotate now, really? So it might, but we didn't have time to think about the teaching angle. Yeah.
Yeah, I think in the interest of time, maybe we can take the remaining questions off.
I'll be happy to answer offline. Thank you all for coming.